Okay, so now we're going to look at implicit differentiation, and we use implicit differentiation in the case where we cannot get y as an explicit function of x. For instance, here's an example. This is the equation of a circle, and if you try to solve this for y, you end up taking a square root, which actually splits it up into two separate equations. The equation of the top half, which is where the principal square root would be, and the equation of the bottom half, which is where the negative square root would be. So you actually get two functions of x. So y is not explicitly a function of x, but implicitly we actually have y represented by two functions of x that share a domain. Okay, so we can still use uh, we can still find the derivative of this function. We just cannot find the derivative explicitly. We're going to have to use implicit differentiation because y is not an explicit function of x here. So what we're going to do is, when we take a look at this notation, the Leibniz notation, I'm taking the derivative with respect to x. That's what this variable here tells us. This tells us the independent variable. And here, I'm being told that I'm taking the derivative with respect to x of whatever function is here, whatever function is there. Now, if that's a simple function of x, like x to a power, or the sine of x, or the cosine of x, then we can use one of the simple power rules. Um, or, sorry, not one of the simple power rules, one of the simple rules. It could be the simple power rule, or the simple sine rule, the simple log rule, the simple exponential rule. But in this case here, for this term here, x to the second power, and this term here, negative 6x to the second power, we can actually use this simple power rule because we have the derivative with respect to x, and then we have x to a power. X itself is being raised to a power, so the independent variable is the one that has the power. Therefore, we can use this simple power rule for those two terms. But for these two terms here, this term and this term, well, in this case, we're going to have to use the general power rule because in those two cases, even though we have a power of a variable, the variable we have the power of is not the independent variable. We're trying to find the derivative with respect to x. So if you're trying to find the derivative with respect to x, and it's not x that you have written to the power, well, if that thing that you have written to the power is a function of x, and we already have determined that y is an implicit function of x on the last page, we actually get two functions of x. So y is implied to depend on x. Changing x would change the y value. Y is not constant when it comes to x, but y does indeed depend on x. So therefore, we can use this general power rule. The general power rule is just the chain rule form of the simple power rule. It says whenever you have an inside function, and in this case, our inside function is y, which is a function of x, when you're taking the derivative, and the outside function is a power function, like y to the second power, for instance, then all you have to do is take the derivative with respect to y of the expression that you see and multiply by the derivative of the inside function, which is in our case would be y. So we're going to use that rule for these two derivatives here. Let's go ahead and take the derivative then. So the first thing, we're going to take the derivative with respect to x of x squared, which this one we can use the simple power rule, and the simple power rule says that that's equal to 2x, right? And then we're going to take the derivative with respect to x also of y squared. Well, in this case, we can't use the simple power rule because the variable that I'm taking the derivative with respect to doesn't match up with the variable I'm raising to the power. So in this case, I'm going to have to use the general power rule because I do know that y is a function of x. So therefore, it does have a derivative or a rate of change with respect to x. So for that case, I'm going to take the derivative as 2y, which is the same here, 2 and then the inside function to the raised to the power of n minus 1, which is 2 minus 1 here. And then I'm also going to have to multiply by dy dx. So this is also multiplied by dy dx. All right, so there you go. That's the derivative of the first two. Now, the derivative of this one. I have the negative 6, which is a constant multiple. But then I'm going to take the derivative with respect to x of x to the first power. Well, the derivative with respect to x of x to the first power, you can use the simple power rule and you get that this is equal to 1. So this is negative 6 times 1, or negative 6. And then this term here is going to be plus 4 times the derivative with respect to x of y. Well, in this case, I still get 1 because I'm taking the derivative of the outside function, but it's going to be 1 multiplied by dy dx, the derivative of the inside function. So in this case, I get plus 4 times 1 dy dx, or plus 4 dy dx. You see, anytime you take the derivative and the independent variable is not the same as the variable for which the rule you're looking to use applies, you have to use the chain rule version of that rule. And in this case, the chain rule version is this general power rule. All right, and then on the other side, this is equal to then the derivative with respect to x of 12. Well, 12 doesn't change if x changes. 12 is a constant. So this is equal to then 0. So uh, here we have our derivative of each individual term. Now we are actually trying to find dy dx. So to find dy dx, all we have to do then is go ahead and solve for dy dx here. So I'm going to, let's see, I have a 2x and a negative 6. I'm going to put those on the other side. So I'm going to have 2y dy dx plus 4 dy dx is equal to, um, this is going to be a positive 6 when it goes to the other side, and a negative 2x. Now I can factor out dy dx out of these two terms, dy dx. And then I have 2y plus 4 here equals 6 minus 2x. And then to find dy dx, I can divide both sides by 2y plus 4. So I get 6x, or 6 minus 2x divided by 2y plus 4 is equal to dy dx. You can actually simplify this a little bit. If you factor a 2 out of the numerator, you're going to be left with 3 minus x. And if you factor a 2 out of the denominator, you're going to be left with y plus 2. And the 2's would cancel. And your derivative would be 3 minus x over y plus 2. And there you have it. All right, now let's take a look at this one. This one is a little bit more complicated, okay? So to take the derivative of this one, the first thing, well, we have this simple sine rule, but that's for the sine of x. Notice that the independent variable matches up with the independent variable of the sine. So we can't use that rule here. That's the simple sine rule. So we resort to the general sine rule, which is for taking the derivative with respect to x, but of the sine of u, where u is a function of x. U is a function of x, okay? So this is actually implied to be the arc sine. So this is definitely a function of x if you restrict it also. So there is an implied function of x there. So y, once again, can be assumed to be a function of x. So we can use this general sine rule to take the derivative of the sine here. And then for this part right here, we're going to have to use the product rule, because remember, we just said that y was a function of x. So we have a function of x. It's actually a composition multiplied by another function of x, x to a power. Therefore, this is a product of two functions of x, which is exactly what we have here. So we have to use the product rule. The product rule says we take the first function and multiply by the derivative of the second function and add the second function times the derivative of the second function times the first function. So we have to find the derivative of both functions. And then this one, that one, well, we're going to use the power rule. Same thing we're going to have to use over here. All right, let's go ahead and take the derivative. So to take the derivative of the sine of y, we have, well, we're taking the derivative with respect to x, the derivative with respect to x of the sine of y. So by the general sine rule, this then is going to be equal to the cosine of y multiplied by dy dx. And then that's equal to, we're going to have here the derivative with respect to x of x to the fourth y squared. And that, for that, we're going to have to use the product rule here. So the first function is x to the fourth. So I'm going to take the first function, x to the fourth, and multiply by the derivative of the second function. Well, the second function, the derivative of the second function, is the derivative of y squared. For the derivative of y squared, I'm going to have to use the general power rule that we saw on the last slide. So that's going to give me 2 times y to the first multiplied by the derivative of y with respect to x, because I have to use the chain rule. All right, and then that's going to be plus the second. The second is just y squared times the derivative of the first, and the derivative of the first is the derivative of x to the fourth. And in that case, I can use the simple power rule to just get 4x to the third power. All right, now to get the derivative of the last thing, this is going to be plus 2 times the derivative with respect to x of y, and that's just going to be 1, but it's going to be 1 times dy dx. 1 times dy dx. All right, so here we have the derivative of each of the individual terms. Oops, and I forgot the 2. It's not just going to be 1, it's going to be 2 times 1 times dy dx. So I have this term, and this term that all have dy dx. I'm going to go ahead and bring them over to the same side. So I'll have the cosine of y times dy dx. This term also has dy dx. This term is 2 x to the fourth y dy dx. And when I bring it over, it's going to be negative 2 x to the fourth y dy dx. And this term, 2 dy dx, is going to be negative when I bring it over also. So it's going to be 2 dy dx. And that's going to equal, but let's see, this is the only term that doesn't have dy dx. So that's going to be 4 x to the third, y squared, y squared. All right, now that I have all the terms that have dy dx on the same side, I can factor out that dy dx, and I'm going to be left with the cosine of y minus 2x to the fourth y minus 2 equaling 4x cubed y squared. And then all I have to do is divide both sides by cosine of y minus 2x to the fourth y minus 2. And I'll get dy dx. So dy dx here is equal to 4x to the third y squared, all divided by the cosine of y minus 2x to the fourth y minus 2. And that is the derivative of that function with respect to x. So doing this implicit differentiation, the key is to recognize when you have to use a simple rule because you're taking the derivative of just x to a power, or the sine of x, or the natural log of x. And when you need to use the chain rule, because when you use the chain rule, you have to have the added factor, which is the derivative of the inside function with respect to x. All right, with respect to the independent variable x. All right, so that is the um, implicit differentiation.